Hey gang, welcome back to 4600. We're moving into section 5.8 today, which is all about the expected value and variance of linear functions. Kind of set the stage here. We won't do a lot of this in this course. There's some chapters later in the book that we won't make it to. So maybe in a future course that you may take, so if some of you go on to graduate school and do stuff with, take a statistical theory course, stuff we're learning in this section will probably come up and be helpful for you in the future. But you may infrequently encounter some parameter estimators. Parameter estimators meaning parameters mu, the mean, the population mean, and the variance sigma, or sigma squared, the population standard or variance. That are in linear functions, like you might want to find it of linear functions. We've kind of done stuff similar to this already, but this is kind of taking it to a different level. So we may be interested in finding these parameter estimators that are linear functions of the measurements in a sample where we have several random variables, y sub 1 through y sub n. And if we have constants, a sub 1 through a sub n, we would need to find the expected value and variance of a linear function of those random variables being that. So an example, kind of a general example of a what I would call a linear function of random variables would be like we'd call it u sub 1 in this case, would equal the constant times the random variable y sub 1, the constant for a sub 2 times the random variable y sub 2, so forth and so on. So it's basically just the sum of however many random variables you have times a constant, all right? And maybe that may be one type of a function. I mean, the functions can be vary depending on what the setup is and what problem you're trying to solve. But we also may be interested in the covariance between two such linear combinations, any pairing of the linear combinations in a set of random variables. And so the results that simplify the calculation on these quantities are summarized on this next slide. So these are some formulas that will be handy to you in this section. And if we have the random variables y sub 1 through y sub n, and say another set of random variables x sub 1 through x sub n, they're just setting up our formulas for us, be random variables with the expected value of y sub I equals mu sub I, and the expected value of x of j equals, now you've probably never seen this symbol. If you have, you've seen it somewhere else. That's another Greek letter. It's called C. It's like pronounced like with a very little K in it, but sometimes people call it chi, or not chi, but C or Kasi is what that value, that variable is. So there's just another variable saying the mean, in this case, of the x of j, of all the x of j's, if you were trying to find the expected value of several random variables x. So that's just another version of mu, if you will, in the way these textbooks do the problems. But if we can define u sub 1, which equals the sum of I equals 1 to n of a sub I times the random variable y sub I, and u sub 2 be the sum from j equals 1 to m of b sub j, x of j, the random variable x, the random variable x of j's, for constants a sub 1 through a sub n and b sub 1 through b sub m, then the following hold. All right, so if you want to find the expected value of one of those guys, u sub 1, then it's just the sum of I equals 1 to n of a sub I times mu sub I. So all the random variables times their constants added together. That one's a pretty simple calculation. The variance one here, it will become clearer how this works. Part B says the variance of u sub 1 is equal to the sum of I equals 1 to n of a sub I squared. So you're pulling the constant out and squaring it from the function itself. And then it's times the variance of y sub I. So however many random variables you have in there, essentially you're going to have a constant associated with each one of those random variables in a linear function. You'll pull that value out, square it, and multiply it times its respective variance for that particular random variable, whether it's y sub 1, y sub 2, yada yada. Then you add on top of that 2 times the sum of all the possible covariance combinations there are between however many random variables you have. So that'll be what they call a sub I, a sub j, covariance of y sub I, y sub j, where the double sum is over all pairs I sub j, where I is less than j. That'll become more apparent what that means. That's kind of convoluted, but you'll see what it's actually a lot simpler in practice than it is in the formula here. And then part C says to find the covariance between two linear functions, u sub 1 and u sub 2. You sum the I sub 1 to n and sum j sub 1 to m of the two different random variables. The two linear combinations. It's kind of almost like you're multiplying the two linear combinations together, as you'll see. But it's a sub I times the b sub j variable times the covariance of y sub I, x sub j. Again, this is not going to make a whole lot of sense until we put it into practice. Once you see how it works in the problem we're about to do here in a few minutes, it'll become clearer. Okay, so we're going to need to kind of remember these formulas, and they're kind of handy. So this very first example is going to kind of, give us a really good clear-cut feel of how to do this problem. So they just went ahead and gave us all the totals. We don't have to do a lot of finding the expected values and the variances for the different random variables. So they gave us the information here that the expected value of y sub 1 is 1, expected value of y sub 2 is 2, expected value of y sub 3 is equal to negative 1, variance of y sub 1 is 1, variance of y sub 2 is 3, so forth and so on. So they've given us all this information. But what they want us to do is find the expected value and variance of the linear function u, which is comprised of three random variables, y sub 1, y sub 2, and y sub 3, such that y sub 1 minus 2y sub 2 plus y sub 3 is what u equals. All right. And then they've given us another one, and we'll do this on another slide here in a minute, but they've given us another one, a function called w, which is just a linear function of 3y sub 1 plus y sub 2, and they want us to use that along with the u linear function they gave us to find the covariance of u and w. All right, so we're going to find the expected value first of the u. So it's not too bad. So based on the formula, expected value of u, and I guess I should just do it, u, is equal to the expected value of y minus 2y sub 2 plus y sub 3. Now the formula is kind of helpful a little bit, but really all it's saying is that we can pull up a couple of things here. That's y sub 1. Really, we could just treat this like we've been doing before. The formula is only helpful to a certain extent. So this is saying the expected value of y sub 1 plus the expected value of negative 2y sub 2 plus the expected value of y sub 3. The y sub 1 and y sub 2 constants, they don't have a 2 out in front, but they're 1 like we have always treated anything. There's always a 1 out in front. So literally this is equivalent to, if you think about it, 1 times the expected value of y sub 1. That's that way the formula is bringing that a sub I variable out front, or that constant, not variable. And then the negative 2 can come out front like we've done in the past, expected value of y sub 2, plus then it would be 1 times the expected value of y sub 3. So it's really just that straightforward. And so we end up just plugging in the numbers we have up there, and it just becomes an algebra problem at this point. Or plugging in for variables. Plus negative 2 times 2 plus 1 times negative 1, which should just give us the expected value of u to be negative 4. All right, and that's all there is to that. Okay, let me undo that and see if I can draw that a little closer, give myself a little more room here. All right, so the variance of u is equal to the variance of y sub 1 minus 2 y sub 2, not lowercase but uppercase, random variable, plus y sub 3. Okay, and according to the formula on the previous page, we can pull out the constants in front of the random variables when we expand this variance, the v, inside the parentheses here, so to speak. And so it's really just, if you the y sub 1 constant's a 1, so it's just going to be 1 squared times the variance of y sub 1 plus negative 2 squared times the variance of y sub 2 plus another 1 squared times the variance of y sub 3. But then here comes the part where we have to add in the covariance parts, all right? So what we do is, since we have 3 of these guys here, we have to treat them kind of like we're pairing them together. You know, it's like 3 choose 2. There's 3 different covariances we have to come up with, and each one of them are going to be similar. So we're going to do 2 times the constant of the y sub 1 variable times the constant of the y sub 2 variable. All right, so that's just like a sub 1, a sub 2, if you will. All right, times the covariance of y sub 1 comma y sub 2. And then we have to add, that was the a sub 1, a sub 2 combination. Now we have to do a sub 1, a sub 3 constant. So we do 2 times 1 is the constant of y sub 1, 1 is the constant of y sub 3, covariance of y sub 1 and y sub 3, plus 2. Now we have to pair the y sub 2 and y sub 3 together, and so we take their constants, so it'll be 2 times negative 2 times 1 times the covariance of y sub 1, or y sub 2 comma y sub 3. So we just plug into this thing, and then we'll have our solution. So that's just going to be 1 squared times variance of y sub 1 was 1 plus negative 2 squared times the variance of y sub 2, which was 3, plus 1 squared times variance of y sub 3, which was 5, plus 2 times 1 times negative 2 times the covariance of y sub 1, y sub 2, which was negative 0.4, plus 2 times 1 times 1, and I don't know, I don't have to write that out. Covariance of y sub 1, y sub 3 is 0.5, plus finally 2 times negative 2 times 1 times the covariance of y sub 2, y sub 3, which is 2. And if you sum all that crap up together, you end up getting 12.6. So a little bit more difficult here, and you got to be careful to make sure you include all the covariance combinations, but that's essentially what that formula was telling us to do. So I paired the 1 and 2, 1 and 3, 2 and 3 together, and then a constant's the same way. So this is a sub 1, a sub 3, a sub, no, sorry. And then the last combination was a sub 2, a sub 3. So not too bad, pretty straightforward. All right, on the next page, I want to make a couple of notes so to find the covariance of u and w, I want to note a few things first. Note that w equals b sub 1, y sub 1 plus b sub 2, y sub 2. That means that b sub 1, according to the original problem, is 3, and b sub 2 is equal to 1, because those were the constants in front of those variables. And we also know that u is equal to a sub 1, y sub 1 plus a sub 2, y sub 2 plus a sub 3, y sub 3, and the 3 constants in front of that, a sub 1 was 1, a sub 2 was negative 2, and a sub 3 was 1. All right. So to find the covariance of u and w, it's literally going to be us pairing. It's almost like taking this function and each term in this function and multiplying it times the term in this function, if you will. So the very first term is going to be, say, a sub 1, b sub 1 times the covariance of y sub 1 and y sub 1. Plus, now I'm going to keep pairing this guy with each term in the w. So again, it's like I'm kind of foiling them together, if you will. Then I get a sub 1, b sub 2 times the covariance of y sub 1 and y sub 2 plus, and now I've finished with that one, and now I do the same thing with the a sub 2 y sub 2 variable. I sync it with each one of the w variables there. And so now I get, let's see, I lost track. My computer kind of went to sleep on me for a second. We got a sub 2, b sub 2, and then the covariance of y sub 2 and y sub 2. All right. Or sorry, I skipped a step there, although that one will be in there too. It should be a sub 2 and b sub 1 first, if you're keeping them in order. Y sub 2 and y sub 1. All right. Plus a sub 2, b sub 2 now, covariance of y sub 2 and y sub 2. So we've exhausted the a sub 2 variable. Now we move on to the a sub 3 and pair it with each one of the terms in the w function. And we get a sub 3, b sub 1, covariance of y sub 3, comma, y sub 1. Plus, finally, we do a sub 3, b sub 2, covariance of y sub 3, comma, y sub 2. All right, which just really equals, we can clean this up a little bit. So the first term is still a sub 1, b sub 1, but the covariance y sub 1 and y sub 1, the covariance of a variable and itself, or of a random variable in itself, is always the variance of that thing, plus a sub 1, b sub 2, covariance of y sub 1, y sub 2, plus the next one is just a sub 2, b sub 1, covariance of, and I'm just going to reverse these because the order does not matter, as we saw in a previous problem. B sub 1 plus, now this term right here, a sub 2, b sub 2, the covariance of y sub 2 in itself is just the variance of y sub 2. All right, and then plus the rest of them stay the same. But I'm going to reorder the y sub variables in ascending order because that's the way they should be done anyway. All right, and so there we got that. We're going to plug into that and we'll get our freaking answer. Oh, it's a lot of this is more these problems in this section are more tedious than others, so I just want to preface the rest of the stuff with that. They're just tedious. And so we get 1 times 3, because a sub 1, b sub 1 are 1 and 3, and then the covariance of y sub 1 and y sub 2 from the previous page, or the variance of y sub 1 from the previous page is just 1, plus a sub 1, b sub 2 is 1 times 1 times the covariance of y sub 1, y sub 2, which is negative 0.4, plus now we got a sub 2, b sub 1, so that's negative 2 times 3 for b sub 1, and the covariance of y sub 1, y sub 2 is negative 0.4 still. That didn't change. Plus a sub 2, b sub 2 is negative 2 times 1, and the variance of y sub 2 was 3 from the previous page. Plus a sub 3, b sub 1 now. I'm doing a sub 3, b sub 1. That's 1 times 3 times the covariance of y sub 1, y sub 3, which from the previous page or slide was 1/2 or just 0.5. And then lastly, the a sub 3, b sub 2. A sub 3 is 1, b sub 2 is 1, so we get 1 times 1 times the covariance of y sub 2, y sub 3, which is 2, I believe. Yes, it's 2. All right, all that work just to figure out that the covariance of u, the linear combination of u and w, is just 2.5. All right, so boom. But since we got that as a covariance between u and w, I'm going to recall one of our former theorems. So since the covariance of U and W is not equal to 0, or that we're doing the contrapositive of the theorem that we learned I think it was last lecture. Yeah, last lecture. It follows that U and W are independent. Now that one didn't ask us that, but this is a good thing to note. Always remember this. Or not independent, dependent, my bad. Or dependent. Yeah. Cool. Well, that's the long-winded solution to that one. All of these are going to kind of be that way, unfortunately. These are just tedious problems, like I said. So, example 2, textbook's exercise 5.26 says refer to examples 5.4 and 5.20. So in example 5.20, we were interested in y sub 1 minus y sub 2. So that's another linear function of random variables. The proportional amount of gasoline remaining at the end of the week is that problem that we did. And then we've seen this joint bivariate distribution function before. Find the variance of y sub 1 minus y sub 2. Recall that the joint distribution was, and they gave us the following. So we did find the expected value of this once upon a time. All right, and so whenever I do one of these problems, what I recommend highly, again, always, you're gonna have to do some double integrals to find some parts of this problem. Unfortunately, you just are. It's an inevitable situation. So we know we're between 1 and 1, and we got the line because of the inequality here. We've got y sub 2 equals y sub 1, and we're interested in y sub 2 is less than or equal to y sub 1. So we're in that region there. So we know how we have to set those things up. But what do we need? Because we've done stuff prior to this. We may not need to integrate every freaking thing to get every part. So the variance of y sub 1 minus y sub 2 is equal to, according to the formula, whatever the a sub 1 variable is squared times the variance of y sub 1 plus the coefficient of the a sub 2 of the second variable squared times the variance of y sub 2 plus, we only have 2 random variables here, so we have to have the covariance in here, plus 2 times the coefficient of the first random variable times the coefficient of the second random variable, all that times the covariance of y sub 1, y sub 2. So there's some things we need here that we did not calculate in previous problems. But I'm going to save us a little bit of time here. Since a sub 1 and a sub 2 are both negative, the formula we really need to solve here, we can just plug in 1 and negative 1 in where we need to. So a sub 1 is just 1, so 1 squared is 1, so we just get variance of y sub 1. A sub 2 is negative 1, but if we square it, it becomes 1, so we get plus variance of y sub 2. And then 1 times, then a sub 1 times a sub 2 is 1 times negative 1, so that 2 becomes a negative, so we get minus 2 covariance y sub 1 comma y sub 2. So that'll be what we'll have to solve at the very end. But from, I believe it was from lecture 5.6, on the lecture over section 5.6, from lecture 5.6, example 5. We know the following. We know the expected value of y sub 1 is equal to 3/4. We're going to need that to find that variance because we haven't found the variance for this thing before, and we need to know the expected value of y sub 2 as well. So that's equal to 3/8. We already found those in a previous problem, so we're not going to do that again. But we're gonna need those here to help us out. So gave us some room to work over here because we still need several things. We need the expected value of y sub 1 squared and the expected value of y sub 2 squared so we can find the variances. Then we also need the expected value of y sub 1 times y sub 2. I told you these things are tedious, so that we can get the covariance value. All right, although I think we might have calculated the covariance value for this before, but we're going to just do it again just for good measure. So I'm going to try to go through these quickly. So the expected value of y sub 1 squared is equal, and remember what I'm going to set all mine up to is I'm going to, using this form over here, I'm going to set all my double integrals up to go from 0. I'm going to go in the y2 direction first and go 0 to y sub 1, and then go from 0 to 1 for each one of these to keep them consistent so I don't have to think about those limits every time. All right. So I'm going to set my double integrations up, and I'm going to go 0 to y sub 1 and then 0 to 1. The original function was 3y sub 1. We're multiplying in an extra y sub 1 squared, so this becomes 3y sub 1 cubed, dy sub 2, dy sub 1. All right, so we can do this quickly, and I won't talk all the way through it. And so we end up getting 3/5 y sub 1 to the 5th, 0 to 1, or just 3/5. So there's the expected value of y sub 1 squared. Expected value of y sub 2 squared, if I put it in the right place, same setup for our double integral limits of integration. This time we're taking the 3y sub 1 and we're multiplying in a y sub 2 squared, so we end up getting 3y sub 1, y sub 2 squared, dy sub 2, dy sub 1. I'm getting the integral 0 to 1 of, let's see here, the y sub 1 is the only thing that's, so y sub 2 squared is y sub 2 cubed over 3, means 3 goes away, so we end up getting y sub 1, and we're evaluating y sub 2 cubed from 0 to y sub 1. And then we get the integral, so that cleans up the integral of 0 to 1 of y sub 1 to the 4th power. Yeah, because y sub 1 cubed is what we get when we plug in that, and then y sub 1, yep, dy sub 1. And that just equals 1/5. Y sub 1 to the 5th evaluated from 0 to 1, which just equals 1/5. So we got that. We need that later. Matter of fact, we can go ahead and calculate the variance of y sub 1. And I will not throw the formula in here, but remember it's the expected value of y sub 1 squared, which is 3/5, minus the expected value of y sub 1, which is on the previous slide, which was 3/4 squared. And that should give us something roughly about like 0.04. We'll just use that for our calculations later. And the variance of y sub 2, so we're going to need that later. Variance of y sub 2 is just 1/5, the expected value of y sub 2 squared, minus the expected value of y sub 2, which was 3 over 8, quantity squared, which equals 0.06. And we'll need that here in a little bit. And now I got to find the expected value of y sub 1 times y sub 2 so we can find our freaking covariance. All right, so again, I'm keeping my limits of integration consistent here, but I'm multiplying in a y sub 1 times y sub 2. So my little 3y sub 1 from the original function on the previous slide becomes 3y sub 1 squared y sub 2, dy sub 2, dy sub 1. So I get 3/2 y sub 1 squared, y sub 2 squared evaluated from 0 to y sub 1. And that's going to clean up to 0 to 1, 3/2 y sub 1 to the 4th power, which equals 3/10. It's just going to equal 3/10. I'll skip that last step. I think you guys know how I got from one place to the next. Hopefully you do. So the covariance we can calculate, and then we can finally get our flipping answer. So the covariance of y sub 1 and y sub 2 is equal to, again, the expected value of y sub 1 times y sub 2 minus the expected value of y sub 1 times the expected value of y sub 2. Okay, and so we just plug in what we got. We got 3/10 minus 3/4 is y sub 1's expected value, and 3/8 was y sub 2's expected value, and that's going to clean up to something about like 0.02. So we're going to need that value as well. All right, so there's a lot of different values we need, and it takes a minute to get them. So getting good at these integrals and setting them up is paramount to solving these problems. So finally, the variance of y sub 1 minus y sub 2, we had rewritten as the variance of y sub 1 plus the variance of y sub 2. In the end of it, we end up getting a really nice formula to plug into, and it's kind of simplified here in the end. All the major work, as said, like I've shown you, is kind of done in the beginning here. But plugging in, we've got 0.04 for the variance of y sub 1 plus 0.06 minus 2 times the covariance of y sub 1 and y sub 2, which is 0.02. And that gives us just 0.06 for the covariant, or for the variance of y sub 1 and y sub 2. If I were to ask you to find the standard deviation, you just take the square root of that value. They didn't ask us to do this in the problem, but it's mentioned in the book, so I'm mentioning it here. And that's approximately equal to 0.245. So remember, the standard deviation is the thing we want. If we were like trying to figure out how many standard deviations, what percentage was, beyond, below and above the mean, doing those kind of interval kind of things. With both Chebyshev's rule, there's a problem in the homework that deals with Chebyshev's rule, where you need the standard deviation rather than the variance, but you got to get the variance to get the standard deviation. So, all right, that's that one. Some of these problems are going to require you to do that much work, if not a little bit more. Sometimes you might have to still find the expected value of y sub 1 and y sub 2, because that hadn't been calculated either. So be prepared to just calculate all these things, because you're going to need them all. This next exercise is from 5.27, and I think it's a good exercise. I'm going to do it a little differently than the way the book did it, because I think it makes a little more sense. But it says, let y sub 1 through y sub n be independent random variables with the expected value of y sub I equal to mu and the variance of y sub I equal to sigma squared. Sounds a lot like a normal distribution, right? And let's key in on the word every time we see independent. That's helpful to us, all right? Especially when it comes to calculating variances. All right, so these variables may denote the outcomes of n independent trials of an experiment. Define the sample mean, y bar, or the mean of the sample means is really what this is, and we're going to talk more about this later on when we talk about sampling. Some of you are probably familiar with this if you had Trimboli for applied stats, and so some of this looks familiar to you because of that. But the random variable y, the mean of the random variable y in this case is equal to 1 over n times the sum of y sub I, which is the formula we know as being your generic arithmetic mean. All right, and show that expected value of y bar is equal to mu, and the variance of y bar is equal to sigma squared divided by n. So we can do that here on this one slide. I want to make a note up here. Note, y bar is equal to, if we think about the way that summation works out, 1 over n times y sub 1 plus y sub 2 plus ... all the way through the y sub n random variable, which in turn equals 1 over n times y sub 1 plus 1 over n times y sub 2 plus ... 1 over n times y sub n. Right? So we've got n terms that look very similar to each other, right? So this makes the expected value part rather simple. So the expected value of y bar is just equal to the expected value of that last thing I wrote above. 1 over n y sub 1 plus 1 over n y sub 2 plus ... 1 over n y sub n. And if we expand that expected value in there, we get we can pull the constant out in front of each one, so we get 1 over n expected value of y sub 1 plus 1 over n the expected value of y sub 2 plus dot 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 1 over n expected value of whatever the y sub n random variable happens to be. Well, that's just equal to 1 over n times mu, because expected value of y sub I equals mu, plus 1 over n times mu plus dot 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 1 over n times mu. All those y sub n nth values all become mu, which is nice. Well, that means we have 1 over n times mu n times, right? So that's n times 1 over n times mu. The n's cancel and we end up with mu. So we just showed that the expected value of a sample of random variables ends up giving us the population mean, is what we just showed. Just using the idea of the linear function concept, which is kind of cool. You can do the same thing with the variance, and we're going to get what we call the an estimator for the variance, which we call the sample. It's going to be called, it's the sample estimator is what it is, or what some of you may have gotten referred to this as the standard error, if you will. So if you've been in a class that you've done a lot of applied stuff in, when we do sampling, we have to usually use the standard error in place of when we sample instead of the population standard deviation, because we don't often know that value. So very similar to this, the variance of y bar is just 1 over n times y sub 1 plus 1 over n times y sub 2 plus, again, dot 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 plus y, 1 over n times y sub n. And if we pull the 1 over n's, which are constants, out in front of each one of these things and expand the variance across the board, then it just becomes 1 over n squared times the variance of y sub 1 plus 1 over n squared times the variance of y sub 2 plus dot 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 1 over n squared times the variance of y sub n. But we're not done, because we have to think about, also we have to add to that dot dot dot, I'll do it on the next line down, 2 times 1 over n times 1 over n times the covariance of y sub 1 comma y sub 2 plus, and we continue on with all the covariance values. Well, recall I underlined the word independent, right? That means every covariance, no matter which two variables you do, if the random variables are all considered to be independent of each other, they're all 0. And so luckily we don't have to worry about this. It goes away because of the word independence. Isn't that great? That's actually fabulous. It keeps us having to worry about that. So we're only concerned about that major part there. So we just end up getting 1 over n squared variance of y sub 1 plus 1 over n squared variance of y sub 2 plus 1 over n squared variance of y sub n. Or should have put dot 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 in there, but ellipses. 1 over n squared. Let me write properly. I'm trying to write too fast. Variance of y sub n. All right. Well, variance of y sub 1 is, as we saw on the previous slide, what they told us in the problem here is it's equal, variance of any y sub I value is equal to sigma squared. So we can replace that in this, wrong way. We can replace that in the formula here with, so we end up getting sigma over n squared plus, or sigma squared over n squared plus sigma squared over n squared plus dot 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 sigma squared over n squared, because that's what happens for each step, which again just equals n times sigma squared over n squared, which becomes sigma squared over n, like we wanted to find. And that is what we call I guess we would call it the sample, the sample. It's the standard error, but it's the variance of that variety of it. Usually in what we use later when we want the standard deviation, we would write this as sigma squared over the square root of n. That would be this would be what we call your standard error. I'm kind of going ahead of this chapter. They're not going to ask you for this. Standard error, not deviation, standard error. And it should be just sigma over square root of n. We take the square root of this guy here. Okay. And so that's useful for us a lot in statistics. We use that value an awful lot. But this is where it comes from, all right, from taking the variance of the sample means of all the random variables. So that's a cool thing, because that's something you don't see every day. You kind of get thrown at you in some applied classes, and you don't really know why it is the way it is, and this is part of the reason why. All right, we're going to do one more here. Kind of backtrack into a discrete distribution we've used in the past. But this is the number of defectives y in a sample of n equals 10 items selected from a manufacturing process follows a binomial probability distribution. Why they decided to give you n equals 10 here, I have no idea. It has nothing to do with what we're going to be asked to do. But what they go on to say, an estimator of the fraction defective in the lot is the random variable p hat equals y over n. Find the expected value and variance of p hat. Again, I'm going to do this a little differently than the way the book did, because I just think it makes more sense logically. But we know that p hat equals y over n, right? So the expected value of p hat is really just equal to the expected value of y over n. But 1 over n is a constant, and y is our random variable in this case. So it's really just 1 over n times the expected value of y. Well, what do we know about the expected value of y from the problem? Well, we know it's binomial, right? It's from a binomial probability distribution, and we know how to find the expected value of a binomial probability distribution if you recall the formula. It's just n times p. So if you know the probability of success, it's just n times that p. So this is equal to 1 over n times p. 1 over n times p, np. And so the n's cancel, and we're just left with p. Well, in statistics, when you're dealing with proportions, the binomial distribution comes up quite often sometimes. And so p hat is what we sometimes call your sample proportion, and just a p, small p like that, is your population proportion. So the expected value of any of the sample of any combination of samples of sample proportions is equal to the population proportion, is what we just found in a very simple way, just using formulas we already knew. The variance of p hat, it can be done very similarly too. So we're just talking about the variance of y over n, which is pulling it out front. It's just 1 over n squared. And again, I don't have to worry about covariance here, because binomial distributions, one of its qualifications is that each trial is independent, so we know that the data, there's no overlap with these guys, so there's no covariance. We don't have to worry about that with the variance, times the variance of y. Does anybody remember what the variance of y formula is? So we end up getting 1 over n squared times n times p times q is the variance formula for the binomial distribution. Again, one of the n's cancel in the denominator and in the top, and the one on the top goes away, so we end up getting rid of the squared, and we end up getting pq over n. And that is also used a lot in when we use the normal distribution in place of the binomial distribution to do like some confidence intervals or hypothesis testing procedures. The standard deviation we end up using oftentimes, what they call sigma sub p hat in most textbooks, is just the square root of p times q over n. All right, so this is the variance, but that's the standard deviation. All right, so useful things to know. All right. So that's it for the lecture part of this. I'm going to go ahead and I will stop and then chapter out the rest of the solutions for the recommended homework exercises. And I kind of went low with these because some of these take a long time to work through, and I don't want to bore you to tears. And so I'm asking you to do 103, 105, and 106, and I will go through these. So stop the video here, go try these out first, then come back and look at the lecture, the recommended homework solutions afterwards. They'll all be in the same video. So see you for those in a minute. Okay, so the first recommended homework exercise was 103. And they went ahead and, very similar to one of the examples I've done already, they went ahead and gave us all the expected values, variance values, and the covariance values for the combinations for three different y sub 1, y sub 2, and y sub 3. And they want us to find the expected value and the variance of the function 3y sub 1 plus 4y sub 2 minus 6y sub 3. So the expected value one's not going to be a big deal at all. It'll take us 2 seconds, or maybe not quite 2 seconds. It'll take us a few seconds. So expected value of 3y sub 1 plus 4y sub 2 minus 6y sub 3 is equal to 3 times the expected value of y sub 1 plus 4 times the expected value of y sub 2 minus 6 times the expected value of y sub 3. So I'm just plugging in a few problem numbers here, and so we get 3 times 2 plus 4 times negative 1 minus 6 times 4, and we get that the expected value is negative 22. And that's what you get when you're just making up numbers. So anyway, that's it for the expected value. The variance, a little more detailed than that. The variance of 3y sub 1 plus 4y sub 2, I'm drawing them lowercase again, 3y sub 1 plus 4y sub 2 minus 6y sub 3. And notice that the 3 is a sub 1, a sub 2 is 4, and a sub 3 is negative 6. All right. And then I'm going to write out the formula first, because I always like to do that to keep myself on track, especially with the covariances. Times the variance of y sub 3. So it's the squared of each coefficient times the variances of each random variable, plus now we have to add in the covariances. So we should get 2. We take the a sub 1 and a sub 2, covariance of y sub 1, y sub 2, plus 2 times the coefficient of a sub 1 and a sub 3, times the covariance of y sub 1, y sub 3, plus 2 times a sub 2, a sub 3. And that'll complete our combinations, covariance of y sub 2 and y sub 3. All right. So we'll just clean that up a little bit. We get 3 squared. Variance of y sub 1 from the previous page was 4, plus 4 squared. Variance of y sub 1 was 6, plus negative 6 squared times the variance of y sub 3, which is 8, I believe. Yes, 8. Plus 2. So the covariance A1, A2, A1 is 3, A2 is 4. Covariance of y sub 1, y sub 2 was equal to 1. Moving on to the A1, A3 combination, we get 2 times A1 is 3, A3 is negative 6. Covariance of y1, y3 is negative 1. We don't even probably really need to write this last one, but just to be for posterity's sake, we do 2 times the A2, A3 combinations, which are 4 and negative 6. But the covariance of y2, y3, apparently those two are independent of each other, and it's 0 here. So we end up getting 36 plus 96 plus 288 plus 24. Yeah, 24 plus 36. And then we get plus 0, which gives us a grand total of 480. So there's your variance for that linear function. And that's it for that one. And we're going to do a continuous one next. The next example is using a function we've seen before. It says in exercise 5.8, we derive the fact that the function of y sub 1 and y sub 2, or the bivariate, or the joint function of y sub 1 and y sub 2 is equal to 4 y sub 1 times y sub 2, when y sub 1 is between 0 and 1 and y sub 2 is between 0 and 1. It's a valid joint probability density function. In exercise 5.52, which I think we did as an example when we did the independent chapter, we established that the random variables y sub 1 and y sub 2 were independent. So therefore we automatically know that the covariance is going to be 0, which is a nice thing to know ahead of time. And in exercise 5.76, which I'm pretty sure we did in exercise 5.76, I'm pretty sure I assigned that one. We determined that the expected value of y sub 1 minus y sub 2 is equal to 0. So we're going to be able to pull some things without having to do so much work here from old things, which is nice. But they want us to find the variance of y sub 1 minus y sub 2, which is which is going to require a little bit of work on our part, but not much. So recall that the variance of y sub 1 minus y sub 2, we've done one similar to this, should be equal to the coefficient of the first variable squared times the variance of y sub 1 plus the coefficient of the second term squared times the variance of y sub 2 plus, and then we need the covariance is the question. We don't really, do we? Because the covariance is 0, so putting in the covariance won't be meaningful at all, so we don't need that. So remember, that's what independent tells us here, is that the covariance equals 0. Y sub 2 is equal to 0 here, so we don't have to add in that last term in this case. So that's basically our formula. We've just got to find the variances for each one, and we'll be good to go. I'll probably bring this factoid in the end here in a moment. So, but recall from one of the earlier problems, I believe it was 5.52, we had to find the expected values. To be able to find this expected value y sub 1 minus y sub 2, we had to find the expected values separately. So recall from an earlier problem that the expected value of y sub 1 was equal to 2/3. The expected value of y sub 2 was equal to 2/3. That had something to do with them being independent. And that we also had to find the variance of, I believe we're in that same problem, we were asked to find the variance of y sub 1, and that became a 1/18. So the things we don't have that we need are the variance of y sub 2. So we need to figure that out. Or we need to see. It may end up equaling the variance of y sub 1, but we'll find out in a moment. Okay, so over here, now recall this one here is the independent one, but there's no specific extraneous things we have to worry about as far as inequalities are concerned. So we're just concerned about the entire area between 0 and 1 and 0 and 1. So this is a pretty simple integrals to do. So to find the variance of y sub 2, we need to find the expected value of y sub 2 squared first. So we already know the expected value of y sub 2. So 0 to 1, 0 to 1. We don't have to worry about any extra inequalities in there limiting us to a certain sector of that square that we looked at on the graph on the previous slide. So we're multiplying in y sub 2 squared times the function of 4y sub 1 y sub 2 dy sub 1 dy sub 2. Alright, which equals just the double integral from 0 to 1, 0 to 1 of 4y sub 1 y sub 2 cubed dy sub 1 dy sub 2. Alright, so not too bad. It's going to be 0 to 1. The y sub 1 becomes y sub 1 squared over 2, so we end up getting 2 y sub 2 cubed times, y sub 2 cubed, yes, times y sub 1 to the second power, evaluated between 0 and 1, dy sub 1, and that, lo and behold, simplifies to just 2 y sub 2 cubed dy sub 2, which becomes 1/2, and y sub 2 to the fourth, evaluated from 0 to 1, which is just 1/2. So the variance of y1 we already knew from the previous slide was 1/18. The variance of y sub 2 is going to be taking the expected value of y sub 2 squared minus the expected value y sub 2 quantity squared, which is going to be 1/2 minus it was 2/3 for the expected value of y sub 2. It's 2/3 squared equals 1/18. All right, so it did end up being the same, which is not always going to happen, but sometimes it does happen. All right, so variance of y sub 1 minus y sub 2, as we found on the previous slide, was just, remember, it was a sub 1 squared, variance of y sub 1, plus a sub 2 squared times the variance of y sub 2, and then it should be plus 2 a sub 1, a sub 2 covariance of y sub 1, y sub 2, if we're being correct here. But remember, this is going to go away to 0 because the functions, the random variables are independent of each other. So we end up just getting a sub 1 is 1, so we just get 1 squared times the variance of y sub 1, which is 1/18, plus a sub 2 squared is -1 squared times the variance of y sub 2, which now we know to be 1/18. I guess minus 0 if we're going to be correct here, and then that's just equal to 1/9. So nothing too exciting there, but nonetheless we were able to find the variance pretty quickly in this case because we had done work on this function before. Okay, so that's it for that one. The next one's going to be a little bit more work to it because we've not done it before, so we're going to go through the whole process on that one. So anyway, see you on that one in a minute. Okay, so the last one's going to be the one that takes the longest here, 5.106. This is a good one to do though, because it's got, some restrictions with the inequality in the original integral, plus we don't know a lot of this information here already. They are telling us and letting us know that the covariance of y sub 1 and y sub 2 is equal to 1/40, so they're kind of giving us a heads up with that calculation, so we won't have to do it again. But they want us to take this function and find the variance of y sub 1 minus 3 times y sub 2. All right, so before we even get involved in that, let's take a look at this here. So we know we're between 0 and 1. No, I'm not drawing it exactly correct, but y sub 2 equals y sub 1. And we want to know when y sub 1 is less than or equal, so we're talking about this area up here. All right, that's the area we're going to integrate from. And so I'll probably go from in the y1 direction and then the y2 direction because I'd like to have a 0 in my inner integral. So when I set my integrations up at this time, I'm going to go in the y1 direction first, so from 0 up to, if I'm going to the y1, it'll be the y sub 2 direction. And then in the y1 direction, I'll go from 0 up to 1. All right, 0 to 1 that way. So that's how I'm going to set my integrals up in this instance. All right, so let's look at the function real quick and see what all we need. We kind of need everything, honestly, except for the covariance, which I will not work out here again because I would like to think you guys know how to do that by now for sure. But variance of y sub 1 minus 3 y sub 2 is really equal to a sub 1 times the variance of y sub 1 plus a sub 2 times the variance of y sub 2 plus 2 times a sub 1, a sub 2 times the covariance of y sub 1 and y sub 2. All right, so that's we need the expected values and the variances, or the expected values of y sub 1 and y sub 2 as well as their squared counterparts to find the variations. If we were going to find the covariance, we would also need the expected value of y sub 1 times y sub 2 to get that calculation. So let's go ahead and start on this page with finding the expected value of y sub 1, which is just going to be the double integral. As I said, I'm going with my inner integral in the y1 direction. I'm going 0 to y sub 2 first, and then 0 to 1 on the outside. And I'm going to go ahead and just multiply this function here by y sub 1. I'm going to think of this as 6 minus 6y sub 2 the whole way through. And so if I multiply y sub 1 into that, I get 6y sub 1 minus 6y sub 1 y sub 2. dy sub 1 dy sub 2. Alright, and that's going to quickly become 0 to 1. And my integral for each one with integrating with respect to y sub 1 becomes 3y sub 1 squared minus 3y sub 1 squared y sub 2 from 0 to y sub 2 dy sub 2, which kind of neatly cleans up to the integral from 0 to 1 of 3y sub 2 squared when I plug in the y sub 2 value for y sub 1 minus 3y sub 2 cubed dy sub 2. So we end up getting, this is y sub 2 squared. The first term becomes just y sub 2 cubed minus the second term becomes 3/4 y sub 2 to the 4th power. And we're going to evaluate that from 0 to 1. And that gives me 1 minus 3/4, which is just 1/4. Alright, so there's one of the things we needed. One of the many. Alright, so now I'm going to go ahead and find the expected value of y sub 1 squared. Again, I'm just going to skip the step and multiply the y sub 1 squared directly into that first function that we had, and my limits of integration are going to stay the same. Figure why not? You can change them up if you want. It's totally up to you. But multiplying in a y sub 1 squared, I get 6y sub 1 squared minus 6y sub 1 squared y sub 2 dy sub 1 dy sub 2, which equals integral from 0 to 1 of first term becomes 2y sub 1 cubed minus 2y sub 1 cubed y sub 2, evaluated from 0 to y sub 2 dy sub 2, which equals the integral from 0 to 1 to y sub 2 cubed minus 2y sub 2 to the 4th dy sub 2. Integrate that with respect to y sub 2, and we should get 1/2 y sub 2 to the 4th minus 2/5 y sub 2 to the 5th. Evaluated between 0 and 1, and that just gives me 1/2 minus 2/5. Thank goodness for the zeros, right? Which equals 1/10. So there's the value I need. So we can find, well, now we know the variance of y sub 1 because we can take that 1/10 minus the expected value of y sub 1 squared, which was 1/4 squared, which equals 3/80. So there's the value we definitely need. I'm going to just box that in red, actually. Got to have that one. All right. So now we need to commence to finding the variance of y sub 2. So again, I need the expected value of y sub 2. Again, I'm setting my double integral from 0 to y sub 2, 0 to 1. Multiplying in a y sub 2, I get 6y sub 2 minus 6y sub 2 squared dy1 dy sub 2. Since both of those don't have a y sub 1 variable in them, they're just all constants, so we get the integral from 0 to 1 of 6y sub 2 minus 6y sub 2 squared times y sub 1 evaluated from 0 to y sub 2 dy sub 2, which equals the integral from 0 to 1 of 6y sub 2 squared, because the plug-in in the y this plug-in in y sub 2, just distribute that, you get 6y sub 2 squared minus 6y sub 2 cubed dy sub 2. Alright, so we can finally calculate that thing out, and we end up getting should be 2y sub 2 cubed minus 6/4 becomes 3/2 y sub 2 to the 4th, evaluated from 0 to 1, so we end up getting 2 minus 3/2 here, which is just 1/2. So there's part of something we need. And then the expected value of y sub 1 or y sub 2 squared, we need that to find the variance as well. Again, double integral 0 to y sub 2, 0 to 1. This time I'm multiplying on a y sub 2 squared, so I get 6y sub 2 squared minus 6y sub 2 cubed, dy sub 1, dy sub 2, which equals the integral from 0 to 1. Again, all that's a constant, times y sub 1, evaluated from 0 to y sub 2, dy sub 2, which just equals the integral from 0 to 1 of 6y sub 2 cubed minus 6y sub 2 to the 4th dy sub 2, which equals the integral of the first one will be 3/2 y sub 2 to the 4th minus 6/5 y sub 2 to the 5th. Looks like an S. My 5s always look like S's. Which equals from 0 to 1, which equals 3/2 minus 6/5, which is just 3/10. So on the next slide, I gave us an extra page for this one because I knew we would need it. We'll do the variance calculation over there. So we need to know that 1/2 and that 3/10 there. So the variance of y sub 2 is just equal to the expected value of y sub 2 minus the expected value of y sub 2 squared minus the expected value of y sub 2 quantity squared, which was 3/10 for expected value of y sub 2. Let me just fix that. Which is 3/10 minus 1/2 squared, which is just 1/20. Alright, and remember, we know that the covariance of y sub 1 and y sub 2 is equal to 1/40 from a previous slide. So now we have every freaking thing we need. Alright, if you're not given this though in a problem, you've got to calculate the expected, if not given, to calculate expected value of y1 times y2, then covariance of y1 y2 is equal to the expected value of y1 times y2 minus the expected value of y sub 1 times the expected value of y sub 2. But you guys probably already knew that, right? So finally we can just go ahead and figure this rest of this problem out and be done with it. Variance of y sub 1 minus 3 y sub 2, as I said before, is equal to, remember a sub 1 here is 1 and a sub 2 is here is -3. So it's a sub 1 times variance of y sub 1 plus a sub 2 is squared. Sorry, did I square it on the original one I did? I did not. Some of y'all probably caught that. A sub 1 squared times the variance of y sub 2 plus 2 times a sub 1, a sub 2 times the covariance of y sub 1 and y sub 2. So that's a pretty simple formula now. A sub 1 is 1 squared. Variance of y sub 1, which we found on the previous slide, was 3/80. Double check that. 3/80, yep. So the variance of the next one is this value right here. A sub 2 squared is going to be -3 squared. The variance is 1/20 plus 2 times a sub 1 times a sub 2 times the covariance, which they gave us nicely, 1/40, which equals 27/80. And that is the answer to that one. So again, it's tedious. It's a lot of work to answer some of these long-winded problems like this, but you know, it is what it is, folks. Sometimes you just got to show the work and go through the process. So it's an unfortunate part of statistics and calculus and mathematics in general. So sometimes you just have to work. But anyway, I hope you guys are having a good one, and we'll talk to you later.